continuous thing. So we're dealing with sheaves. And as you know, this is just mapping. So a sheaf is a mapping from open sets to, for example, leading groups. And the usual two axioms are fulfilled. And then you can piece together. So S alpha restricted to U alpha beta equals S beta restricted to U alpha beta. It means that you can find a global one on the full space, say, on the full space axis, where you have a covering with S restricted to U alpha equals S alpha. That's the piecing together, what I call piecing together. And then what we have here then is S is a section on X of the sheaf. Sometimes I write script here just emphasizing the sheaf space. And similarly then the identity principle in some sense. So if the restriction of S to U alpha equals the restriction of T to U alpha, then for all alpha of course, then that's T. So piecing together and uniqueness. So that's a sheaf. And we have exact sequences of sheaves, so short exact sequences, like here. You will use them constantly in this business, but just as a general short exact sequence, I quite often map it like this, three sheaves. And this means really exact at the local level. For example, we talked a great deal about the subjectivity or what it really means. It means that you're given a point, you're given a germ, you extend it someplace, then you're allowed to, you want to find something that goes on to it, but you're allowed arbitrary shrinking to find something that goes on to it. So this is short exact sequence of sheaves.
Is it the same as, would it be equivalent to saying that at the level of stocks?
That's right. It's just at the level. You have to understand what the stock really is. It's a direct limit object. Right? We talked about this. A direct limit object, no, or inverse limit. I'm never sure. Right. It's exactly that. And an example that I want to talk about, it really exemplifies plenty, is the following thing on a one-dimensional Riemann surface. The following thing, I'm going to write it and then I'll recall the notation. Here's a very interesting exact sequence. So I look at O and P. Thanks. So we have this Riemann surface. Maybe something like this, and we have a point P here, and we look at a very important sheaf. This is the sheaf of germs of meromorphic functions M, whose divisor of M, so that's just what it defines as a divisor, is bigger than or equal to minus NP. This means that at the point P, M locally, at the point P, if we have some local coordinate, say Z is the local coordinate here, then locally in that coordinate, M of Z is allowed to have poles, but at most of order n. So A minus N, Zn plus A minus 1 Z plus constant plus higher order term. Okay, so the divisor of M has poles possibly, but no worse than N. And we talked about yesterday. Okay, that's a very important sheaf, and this sheaf injects into the same thing with poles of order n plus 1. Clearly, if you have something of order n at worst, then it's of order n plus 1 at worst. So that's a sheaf injection. That's completely clear. And then the quotient sheaf, these two sheaves are exactly the same except at P. But at P they differ exactly in the nth order. So what we get here is just a sheaf which is supported at P. But really it's just the nth plus 1 order coefficient identifies this with the complex numbers at that point. Otherwise the quotient is just 0. So we get this short exact sequence. Okay? We get that.
But isn't it Cn?
No. So this means that if this is the local expansion, this means that this thing is in O and P, and MZ having a local expansion allowing poles of order n plus 1 means that it's in, you got it right. Means M is in O n P plus 1. I'm sorry, n plus 1P. And this is the only difference that you have here between the two, right, in the quotient. So it's just that coefficient. And it's not canonical, this identification, because I needed a coordinate to write down these Laurent series. But it's isomorphic. It's just one dimension. Now, given a short exact sequence, such as this, we constantly go to the associated long exact sequence in cohomology. And I'm now going to explain that. Okay? And once we have that, we will have very strong results which lead to existence theorems of meromorphic functions that give us certain poles. So, this cohomology is called Czech cohomology. Czech, I think was probably Polish. There were many people in the foundations of mathematics in Poland over the years. I think probably this is, I'm not sure the origin of this is maybe even pre-World War II. So what I'm going to explain to you is quite often we do not write the Czech here to remind ourselves of Czech. So I'm going to explain to you what is the Czech cohomology, the qth Czech cohomology of the space X with coefficients in a sheaf class. And we will have these sheaves here as examples. Okay, so for any cohomology theory, you have to have cochains, cochains. So what are the cochains? So it's you start a cochain associated. So let's say the space of cochains associated to a covering. I showed you yesterday how these things really arise in applications, and they arise in applications on a covering. So a cochain associated to a covering. Let's say U. Our space X. Okay. Well, these things are horrible notation, really, quite frankly. So Q, so I'm going to talk about Q cochain with related to the covering in the sheaf S. Okay. So an element here, maybe it's something C. I'll write it down algebraically for you in a minute, but I'd rather just write down the elements. And this is a collection which I quite often write Si0 to SIQ, starting always at 0. So this stuff is very notation intensive, so please use my notation. So you start at 0. So even though it's a Q chain, you're going to start the index here at 0. Okay? And this thing, so it's over all I with length Q plus 1. So I is the index set. It's a vector, I0 through IQ, and we look at all possible i's here. And what is this? Where this thing is an element of, it's an element of the sheet, so a section is the way I'm thinking, or on the open set, UI0 through IQ. And just to remind you of my notation here, which I use probably extensively already, this is just the intersection. Okay. So a cochain is a formal thing. To every intersection of length Q plus 1, you have an element of the sheet. Okay?
So it's every non-empty intersection. Or
That's a perhaps non-formal point. I never know what the empty intersection is. I think it requires 0.
okay. Oh, I see. Okay.
I think empty intersections probably allow you. You have to.
Okay, that's.
And here we will use the alternating cochain. It's just very, very, very convenient. You can get around using these alternating cochains. If you like, I will. It's just if you apply a permutation to the indices here. Right? I mean, these things are ordered, unfortunately. I0 through IQ, right? If you apply a permutation to these indices, the sign of the permutation hits the thing. So, if you like, sigma is a permutation, so sigma maps I to I, and therefore what you have then is S of sigma I0. So I mean it's just the same thing, but with the sign of the permutation times this thing. So we want to do alternating check cohomology. It's just the right thing to do. Okay. Sorry about this, but that's what it is. To every intersection, you have some section. And we should keep in mind we're trying to glue these things together if we're lucky. And so it's a very natural thing to think about. Now here it comes. The boundary operator from check alternating cochains on a covering of the sheaf to the, it goes up. Cohomology, the boundary operator goes up. So it's always, it comes back to somehow Stokes, and this comes back to then some alternating thing. And I will write it here. The boundary, Q, and let me use a Xi as above. So Xi is a collection of these things, let's say S, I0 through IQ, and I want to know well, where does it go? It has to go to this Q plus 1 place. That means Q plus 2 intersections. So I have to have someplace here let's see, q plus 1 intersection, so let's see if I get this right. J0, jq plus 1, yeah, equals the restriction mapping of S J0, well, I have to sum it, sum minus 1 to the k of S J0, JK not there, JK plus 1, Q plus 1, restricted, of course, to the intersection where it's supposed to be, so J0 to the JQ plus 1. This is a pain in the neck. Let's just, this is what it is.
It's DQ. Okay.
Something? No? So, I'm sorry. So this is the cochain at the qth level. To every intersection, you have a section. And now I've got to get something to every intersection. So this is running over all these indices. And now I have to find out what happens at a precisely given intersection J0 through JQ plus 1. And here it is. It's just you restrict from the bigger set to the smaller set. And the bigger set only has Q indices, so you have to cut out one indices from the Q, one index from the Q plus 1 and restrict it. Of course, you add all these things up. Okay. So let's just make sure, as an example, so the boundary, let's see, let's take a one cochain, which is of the form Fij. Let's see, the boundary of a one cochain, which is the form Fij, on, of course, where does it have to be? U, I don't know, J, equals, what is it? So I have to leave out the first one with a positive sign, so it's FJK. Then leave out the second one with a negative sign, so it's FIK minus. And leave out the last one with a positive sign, Fij. Of course, all of this stuff restricted to Ijk. Right? Now, if you write that in another way using the alternating property, look what that means. It means that Fij plus Fjk plus Fki equals 0. This is a very natural condition. You have three sets, and they intersect. Here you have an Fij, here an Fjk, here an Fki, and this is the cyclic thing on the threefold intersection here. That's just life, and that's the way it is. And as I indicated yesterday, it's very, very important for the applications. Not just, you will see today, this is not just formal. So what we have here is the Q minus 1 chains of U for the sheaf, boundary operator, the Q chains, the sheaf, boundary operator, the Q plus 1 chains, and of course, as we know, this is a complex. Formal check, this is complex. Okay. And of course then, let's just be precise. So the Qth cohomology. The cohomology of the complex is the check cohomology, and so that means that the Qth cohomology is just the kernel of the thing up there, so that's dq. Let's emphasize where it's going from CQ to CQ plus 1. Okay? Yesterday I indicated why that's a good thing to study from the point of view of solving certain problems. Right now it's just a theory that you introduce, objects that you introduce. These things are horribly infinite dimensional. I mean, they're just unbelievable. But you will see today that in applications this is finite dimensional. And that's very, very fundamental. Okay. Now that's of a covering. We're not finished, unfortunately, so we need to define this cohomology of X, and you guessed it, it's a limit cohomology, so it's the limit over the partially order defined by part over all covers, using the partial ordering defined by inclusion of these things. So it's just you take refinements and go to the limit. Okay, that's great. Now, yesterday I sort of indicated what the long exact sequence is, and to prove it using coverings, and to prove something using coverings, you need some theorem which is called the Ray theorem. So, the Ray theorem you know the story about Leray, I guess. In case you don't, I'll remind you of it. Leray, of course, this is a French name, he's a French guy. He was taken to Austria by the SS in World War II. Do you know this story? And he was an applied mathematician and did have work in applied mathematics, interesting, non-trivial work. But he did not want the guards to know that he was an applied mathematician because they would use him. So he became incredibly abstract and invented all this. And taught courses in the prison camp on the subject. And of course these guards couldn't care less about chief cohomology. Well, it's really fundamental what this man did. I mean, there was nothing before the war, and at the end this theory was developed. I mean, and what's the point? Well, the rough statement is if U is acyclic, so then the cohomology, the whole thing with coefficients of U equals the cohomology of the coefficients. I haven't told you what acyclic is. Thing you don't like it. You want to know what acyclic is, yeah? Yeah, because this is a good, whatever it is good. It means you don't have to go to this horrible direct limit, right? Or inverse limit, I don't even know. Well, acyclic means that the cohomology of all intersections, and you can refine this statement, but the cohomology of these intersections are all zero. All intersections. And that is not needed completely. Let me tell you what is needed. You need a triangle. You need a triangle for H1, you don't need much, and for H2 you need twofold intersections, for H3 you need, okay? So you can read this. And this theorem and all formal stuff, so this and all other details about this stuff are presented in compact form. In the context of analytic geometry, in Grauer and Leonard's book on Stein theory. That's a big book. Well, it's not a big book, but it has a lot of content. you should only read chapters A and B. I don't know, Qaisar did this, right? I mean, it's not bad, right? Everything is there. So I'm hiding a lot of the details here in this, but in particular, the Leray theorem is proved there and so on. So it's called Stein theory. It's in paperbacks, and it's recommended reading. I think it's a good book. Okay, so the theorem is this. You have a long exact sequence. Associated with a short exact sequence of sheaves. And it's, wow, usually this is what's going on. You want to say something about sections. So you set up some problem at the level of sections. And then you have some going up mapping as usual. So in every cohomology theory, you have what I call the going up, or people call it the boundary morphism. So this is the going up mapping. And I like to write them things downstairs when you have the first cohomologies. These mappings here are defined in a trivial fashion. So from here to here, from here to here, defined in some completely trivial fashion. You can see it for the exact sequence. But the going up mapping must be defined, non-trivial. Go up to the next level, H2, and so on. And so you get some huge long exact sequence. Usually you know where it stops. Yesterday, what this could possibly be. On a covering I did this example. And now it looks like this is purely formal nonsense, but it is not. Okay. I will prove today, and maybe even still this morning, that the following theorem, originally proved by Qaisar and Sayre, and I will give a proof only for vector bundles. If S is a coherent sheaf from all modules, on a compact complex space, X, then HQ S is finite dimensional. This is not true in the non-compact setting. I will give you an example right now, okay. Which is a nice exercise if you have any interest in doing exercise. It's a nice exercise. So example. So let me repeat again: a coherent and a sheaf, and I will only deal with this as a sheaf, in a concrete case, a sheaf of germs, sections in the vector bundle. Or holomorphic sections. this is the main example for us. So here's an example, H1 of C2 minus the origin. A very important example, actually, the coefficients in O. H1, if you remove the origin, it introduces highly non-trivial things. Is naturally isomorphic to Laurent series, Laurent polynomials. In the coordinates. So the negative, let me just put the negative parts of, that's what I mean, non-trivial, negative part of Laurent polynomials in the coordinates. So this is highly infinite dimensional. Okay, so you can just check this by making it covering and then writing down the Laurent series and showing what's you can just check. There's a good covering of this that satisfies the array and so on. So the covering that you use, just to remind you what you should do if you want to have some fun, is here's C2, here's the origin. This is C2, and the covering you use is, say this is Z0 axis and 0, 1 axis. So U0 is C2 minus Z0 equals 0, and U1 equals C2 minus Z1 equals 0. These are two open sets that cover this. And you can check that the Leray theorem is applicable here. So you only need to compute with this covering. So, okay, so what's given here is you're given Fij, which is, well, F01 here, which is a section of holomorphic functions on the intersection U01. Well, U01 is the intersection of these two things, so it's C star cross C star. And now we're close because you see this has a Laurent development on C star cross C star, and you easily check that the stuff that cannot be written, what you want to try to do, this thing's automatically closed, so you want to check that if it's a boundary, that you can write it as a difference of two things, and you see that exactly the things you cannot write as a difference of two things are those in the Laurent development here, purely negative terms. You can kill off the positive terms, that's easy, because positive terms mean it's holomorphic, all these things, but with purely negative terms, you can't kill it off like this. Okay, so it's infinite dimension. So the first slightly non-trivial example you look at is infinite dimension. Now before I prove the finiteness theorem, and I will give the proof of Brauer of this finiteness theorem, which is very beautiful. So the proof is even more beautiful than the result, because it focuses on the correct analysis. And the analysis is Fredholm theory in a Frechet context. So the theory of Fredholm operators, I will explain to you that a little bit. This means analysis. And this is due to Laurent Schwartz. And the Frechet context, you will see in Frechet spaces, you learn in functional analysis, Hilbert space is good for quantum mechanics, right? So Banach space, you have norm and so on. But almost no space is Hilbert or Banach. Almost every space is Frechet, or limit of Frechet. You see, C-infinity functions are not Hilbert or Banach, right? Anything where non-compactness is involved, you simply, unless you have some measure where you're cutting off things and integrating and making a Hilbert or something. Very rare. Frechet spaces, which I'm now going to talk about after the application, are the fundamental spaces. So doing functional analysis on Frechet spaces or limits of Frechet space, they're really the right thing to do. Yeah. Okay. So let me do an application of the finiteness theorem. We call this the finiteness theorem. So everything is finite dimensional. Say in the context, which is very simple, of course, in the context of Riemann surfaces. So in that context, you have a Riemann surface X, say X. Okay. And now I'm going to take this short exact sequence that I had there. Please pardon me for writing it again. I'm not efficient. This quotient sheet just has support at one point. Here. Okay, the first point that is easy to see is that there are some remarks that anybody can check in spare time before breakfast, is that these things of this skyscraper sheet vanish for Q positive. It's just a formal thing. You can just check the covering and so on, just check it vanishes. Okay, that's nothing. Secondly, you can easily check also using, for example, the Lebesgue covering theorem, which you can really cover a Riemann surface by coordinate charts, for example, disks, so that you have at most threefold intersections. You know that, right? You know, the Lebesgue covering theorem says for a manifold of dimension n, you can cover by charts which would have at most, I hope, n+1 intersections. You can see the picture, right? Lebesgue covering theorem. Covered by disks, you can easily check that these. I'm going to check it later today, just for fun, for you, that that's really a Lebesgue covering. So, the Lebesgue covering. So, by disks, for example, coordinate disk with at most, so when you have threefold intersections is possible, fourfold is not. Okay, then all of this cohomology vanishes beyond so, but got this right. You can easily check that by that HQ X of a vector bundle, any vector bundle, doesn't matter, equals 0 for Q bigger. And this is a completely general thing in the dimension of the space. So that means that not only do you have finiteness, that it stops someplace. Just check it. Okay. Great. So now, if you have a short exact sequence, then what you've got here of sheaves, and you have the long exact sequence of cohomology, what you want to do is introduce something called the Euler characteristic of the sheaf, and that is the sum, as you might guess, of the alternating sum of the dimensions, complex dimensions of these things as vector spaces. Vector space situation of HK of S. So the dimension of the first thing minus zeroth thing minus the dimension of the first thing plus the dimension of the third thing. Okay. In the case of a topological sheaf, for the constants, for example, this is the alternating sum of the Betti numbers, which is the topological Euler characteristic. So this makes sense to call this the Euler characteristic. Okay. Okay. So this is an invariant of great relevance of the sheaf, namely the alternating sum of the dimensions of the cohomology. And now the fundamental point is that you can check again before breakfast without logging on to the internet and looking it up in Wikipedia. You can check it yourself that the Euler characteristic given this short exact sequence, you have the long exact sequence in cohomology, and you have all the cohomologies of the various S prime, S, and S double prime in this long exact sequence. And the formal theorem is that everything here is finite dimensional, so we can add and subtract and so on. The alternating sum of the order characteristics is 0. This is just checked. Okay. You just wake up and you say we have a short exact sequence of sheaves, long exact sequence of cohomology. In the case when things are finite dimensional in a reasonable situation, this quits at some point, so you can write an alternating sum, it's only finite in many things. That's called the Euler characteristic. And then the alternating sum of the Euler characteristic is 0.
Would the zero alternating sum still be true if we have more than 3?
The acoustics is bad and I'm half deaf.
Like if we have more than 3 S's, like for a finite number of sheaves among in an exact sequence like that, like 0 to S1 to S2 to S3, blah blah blah. To Sn.
Oh yeah. Okay. So I think I understand what you're saying. Yeah. So I think what Thane is saying is, I mean, I've looked at a short exact sequence here only, and you could have a very long exact sequence which appears. It will appear. I mean, yeah. And so what you do is, of course, you break it up. Do you see what I mean? You have this big long exact sequence, and then of sheaves. I think what you're saying, Thane, let me write down what I think you're saying. You could have this something like this. Yeah? And so on. Okay, so that means you have everywhere here the sheaf level image equals kernel. So what you want to do is replace this thing by the image. You see? So some image here, it goes surjectively, and then you inject that image in here and you go down here. So you break it up, and you see what I'm saying? You just break it up into short exact sequences and then see what it has to do with the big thing. Okay? Right? So if it's surjected, this goes to its image here, so it's just formally surjected. Right? And so what you do is formally, it goes to this image here. This image is contained, well, you will like pictures like this thing, right? Right? That's all. You make pictures and you have things, and then it gets complicated.
Looks like the alternating sum may not be 0 in this case.
No, I think it's 0 in that case also.
Well, yeah, you have to know what it means, because you only have the long exact sequence for a cohomology associated short exact sequence. Okay. This is just some formal point, but you'll see now it's not formal. So somebody asked us, I think we were talking about, is this stuff formal or is it not formal? So what I'd like to show it is not formal, simply using the finiteness theorem. Okay? Simply using the finiteness theorem is not formal. This is all to this point just formalism, but simply using the finite, you have to. So we have a research group with physicists. In quantum field theory, quite often these people just write down a lot of formal stuff. And in our research group, we don't like that. And at the end of the talk, we start screaming at these people because physicists scream. And one of the favorite things that we scream is, where's the meat? Right? Where is the meat? There's no meat here at this point. You have to put some meat into this. You will see the meat is the finiteness theorem. That is really meat. Right? It is a deep statement that these cohomologies are finite dimension. Okay, up to this point it's just formal nonsense. Not nonsense, it's just language that isolates important things. The meat is the finiteness theorem. thing you learn in this course, at least for Riemann surfaces, for compact Riemann surfaces, there are precisely two pieces of meat. The first piece of meat is the finiteness theorem, and the second piece of meat is Serre duality. Okay. Using these two things, I will explain Serre duality. Using these two things, you prove a huge amount of beautiful, beautiful result. The next piece of meat is Abel's theorem. I talked about yesterday, I think. Okay. Those are the three pieces of meat for compact Riemann surface. Finiteness, Serre duality, Abel's theorem. In higher dimensions, life gets much more complicated. I hope I can get a little bit to higher dimensions in this course. But it's possible I cannot. It's always much more than I think. Okay, so we have the short exact sequence. I'm going to repeat this for the third time today. I'm sorry. We can start here. So I have the Euler characteristic of this sheaf minus the Euler characteristic of this sheaf. Euler number, these are numbers now. Euler number of this sheaf. Plus the Euler number of this sheaf. Now I can even compute this right away because the dimension of the sections, this is just a complex, any complex number defines a section. It's just in this one stalk. That's it. And then there's no higher cohomology, I just told you that, so this is 1, and it equals 0. Okay? Okay. Now, let's go. I want to compute something here. I'm going to look at this long exact sequence a little bit. So what we have H1 of X, O, and P, and H1 of X, O, n plus 1P, down to 0. Actually, I may not even use this Euler characteristic. I will use it all over the place in a minute. I think here maybe I won't even use it. You have to agree, this has no cohomology at H1, so the next thing here would be H1 of the sheaf, and so this is surjective. Okay? This is a finite dimensional space. Well, this is surjective. This is surjective onto that, and then actually, obviously, by just letting n vary, I get a sequence of surjective maps. Right? I don't want to write it; it gets on my nerves. So H1 with 1p goes on to H2 with 2p, goes on to H1 with 3p, and so on. Right? Right? It says that H1 of X np is, well, let me write it in terms of numbers. I write it this way. H1 is ONP. Let's introduce this, which by definition is just the complex dimension of this vector space. Okay? That this sequence of numbers, ONP, is a decreasing sequence. Right? Because it goes down, goes down, goes down, goes down. You don't like this, Mia?
No,
You didn't know listening. This is just formal nonsense for you.
no, I'm lost.
Why are you lost? You shouldn't be lost. You just don't like it, so you go to sleep.
No, I try to find more explanations here.
Yeah, this is a good explanation. You have a short exact sequence of sheaves. This associates the long exact sequence of cohomology. Nobody gets upset about it. And these cohomology spaces are finite dimensional. And at the second level, you get surjectivity here. But the surjectivity means that this is a decreasing in terms of dimension sequence of vector spaces. Yeah? And eventually that means, I don't know that it goes down to 0. I can't tell you that right this minute. It will, by the way. But eventually it stabilizes, right? You go down, down, down. Eventually it stabilizes. Okay? So for n bigger than some number n0, it implies that this doesn't go down. It implies that these two things are isomorphic. That this mapping is isomorphic. It has to stabilize. Right? That means that this mapping here is isomorphic. It doesn't have a kernel. It means, I'm not going to use the order characteristic, it means the mapping doesn't have a kernel. So let's go and see what happens. Sections of O and P, sections of O n plus 1P. These are evaluation map and CP. Next step is, in general, this. It goes into this. But its image is the kernel of this mapping. And the kernel of this mapping is nothing, so this is the global exact sequence. Okay? This says that this space is one-dimensional bigger than this space. Okay? Let's really look at that, because you see this is really an incredible piece of meat. It says, for n bigger than some number, there exists a global meromorphic function on X with the local expansion m of z equal a n plus 1 over z to the n plus 1 plus all the way up, I don't know, with this thing not equal to 0 and with m holomorphic on X minus this point. Right? I think it's fundamental to try to understand this, even if you don't like it. Right? I mean, if I told you at the beginning of this course, given a compact Riemann surface, there was such a meromorphic function, you would have been very, very happy. I've constructed for you not only a meromorphic function, but a meromorphic function that's holomorphic everywhere except at this point. And I prescribed effectively not the full negative Laurent development, but at least after a certain point I can prescribe it. Right? There are only finitely many obstructions that you see in here that you can't prescribe exactly, but here you can prescribe everything. Please, let's look at this. Okay. I want to repeat it because it's new for you and maybe it looks like something out of outer space. Let's repeat it. There is a cohomology theory that works in the following sense, that the cohomology spaces are finite dimensional. You apply it in a stupid way, and you write a long exact sequence, and I'm going to write it again. And then Kayvon's going to explain this in another way, and maybe then, okay, because I know you understand. So, this cohomology theory works, and associated to this thing, the short exact sequence of wonderful little sheaves, I'm going to write the whole cohomology sequence. So sections, that means meromorphic functions with these kind of poles allow. Sections with slightly more general poles allow. Evaluation mapping, literally at that point. First cohomology mapping. This is the non-trivial mapping going up. Then the trivial mapping. And then because it's a skyscraper sheaf, it stops. This is something you can do before you wake up in the morning and not think about. This requires no thought. This is nothing. Okay? Now, these spaces are finite dimensional. Yes? This is a surjective map. That means the dimension of this space is bigger than or equal to the dimension of this space. Right? That means as n varies, this dimension, which I defined, is just the dimension here, this thing. This thing, this dimension, is a very interesting invariant. The dimension of this cohomology space. And the statement is, because this is the surjective map, that this sequence is decreasing. Yeah. So far, have I explained okay? You have a decreasing set of finite numbers, it stabilizes by deep thought. Even if you're completely drunk and lying on the floor, if you have a discrete sequence, right, of positive numbers, it stops. It stops and they are equal. If they're equal in dimension, this mapping is an isomorphism. Yes? A surjective map between equal dimension vector space is an isomorphism. Am I okay, Kate? If this mapping is an isomorphism, it means that it doesn't have a kernel. The image of this mapping is the kernel of this mapping. This mapping doesn't have a kernel. By stupid thought, which you can have, even my granddaughter can have at age 11, this mapping is surjective. Forget all that other stuff. This says that this space embeds in this space in codimension 1. What is this mapping? This is evaluation of that coefficient, the n plus 1 coefficient. This says that this thing has something in it that this doesn't have in it, namely at the n plus 1 order. Well, there it is. This is meat. Spelled in capital letters, M-E-A-T, flash, hot dog. Yeah, this is not just some pancake or something. This is really heavy meat. Right? Given a compact Riemann surface, and given a point on the surface, there is a meromorphic function which is holomorphic on the rest, and almost has prescribed poles, the Laurent development. And you see, yeah, okay, you want to say?
Is there any way to control n0 to know where from each point it's...
Yes.
Because I mean, this argument is not like...
This is very soft.
Right.
This is very soft. And now what you need to know is somehow what's going on in here, what are these cohomologies? More precisely, you want to know what are these cohomologies. But you see, in some sense, what is happening. If the mapping is surjective with the kernel, right? With the kernel, say if it's at the kth place with the kernel, and you want something here in AK or AK plus 1, you're not going to get it, right? Those are the numbers you're not going to get in the negative Laurent development. So it's really trying to understand this mapping here. Well, it's not here. Excuse me. It's this mapping here, right, between these finite dimensional vector spaces. So that's the fine theorem that requires understanding the vector spaces. Yes. But the rough theorem of finiteness tells you there are only finitely many problems. Okay, I think we're okay, right? Okay. So now that's that. Let me start now on proving the finiteness theorem. Okay. Again, There are 3 theorems in Riemann surface. Riemann surface is a very, very simple-minded case because there are only 3 theorems. The 3 theorems are finiteness theorem and some way of trying to understand these cohomologies here in detail. And the way is called Serre duality because these are dual spaces of sections. That's the way to understand them. And the 3rd theorem is Abel's theorem. Okay, I will not prove Abel's theorem, but I will prove the finiteness. Let me start.
Professor, I tried to follow, but
Yeah,
I got lost really at the beginning somehow, because is there any reason for why you changed the capital S in the sheaves with a script S? Why is that? I mean,
No, that's a reasonable question.
it bugs me
Yeah.
badly. I don't understand why did you change that.
Yeah. It's a reasonable question. I changed, so the pre-sheaf, script, not script S, what do you call that?
Capital S.
Capital S. I use capital S for the pre-sheaf. That associates to every open set something. Okay. Now, we take the inverse limit construction by using the restriction map to get a sheaf space with these germs that I drew. Yeah? And that sheaf space is called script S. Okay?
Isn't it the same space?
No. So let's talk about it. Your question is, of course, as always, very good, but
No, I think it's a stupid question. Since
no, it is.
We got
stupid.
here and I still don't understand.
Yeah, no, but it's look, it's notational only, and therefore maybe some people might regard it as stupid, but I don't. It's just a convention, maybe. So the pre-sheaf notation, it associates to every open set some, let's say, a Abelian group or vector space or something. Okay, that's okay with you, you don't mind that. Okay. And then what we do here is we make some inverse limit over refinement of SU, so over all U's, and this is the sheaf of germs at the point X.
Professor, I think it's direct limit.
What?
It's direct limit, I think.
Is the direct limit?
Yes.
So, it depends how you, yeah, okay, so anyway, by refining, you have this equivalence relation, right? You're okay on this, just germs of these things. And we use the script thing, okay?
So why isn't this a vector bundle? It looks like a vector bundle to me. But is it?
No.
Why
No.
is it?
No, well, I understand what you're saying. But don't forget, say, if this sheaf is the sheaf O of holomorphic functions, at a point, this is a sheaf of germs of all holomorphic functions. At that point. That is all convergent power series at that point. Okay? So, and the topology of that, I mean the set theoretical topology of that is spazio lasagnato. That means the open sets are local sections. So it really, the topology is very, very weird. So I recommend you don't think of it as a vector bundle, okay?
Yeah, but it looks like a vector bundle.
It's because you see stalks lined up like that. That's
Yeah.
the reason, okay. But first of all, the stalks are hugely infinite dimensional.
Yeah.
Second of all, the topology is not, maybe you could put some crazy topology, unnatural, make it a vector bundle. But the correct topology is spazio lasagnato topology. It is the open sets are sections, okay? And that somehow is, we say, the associated sheaf. However, if this thing satisfies the two axioms, that these two things are so closely related because you can go to the space of sections of the sheaf and you get this thing back. So it's the same. On the other hand, when we're talking about a short exact sequence, it is mandatory that we're talking about that as short exact sequence of sheaves, because we're always refining, right? Remember the argument. I mean, what does it mean surjective here? It means you take a germ, extend it a little bit, because it's a germ you can, and then see if some extension comes from the other place. So you really want to think about this in this direct limit thing. Okay? So that's...
But a vector bundle is a sheaf. I mean, the other way around. A vector bundle is a sheaf.
A vector bundle is a sheaf in the following sense. Start with a vector bundle, and then look at the sheaf of germs of holomorphic sections of the vector bundle, and that's the sheaf. And I see why you're thinking that, but yes. Okay? And I agree completely. I mean, I'm now beginning to see how it's confusing. If you have a short exact sequence of vector bundles, that's completely what it means, clear what it means. It's just a mapping of vector bundles with short exact sequence, right? Fine. And that is the same thing as the short exact sequence of associated sheaves of germs in the local section. So it's closely related. Okay.
I have to think more about it.
Right now, just accept that sheaf is a good thing. Okay? And, okay, now what in the devil am I trying to do here? I
No,
forgot.
because the terminology is what confuses me. So you say a sheaf of sections. When I think of a sheaf, what I think is that I have the space below, and I have sheaf, okay, like a vector bundle. And the sections are things that go horizontally, not vertically. And when you say sheaf of sections, then I
Sheaf of germs of sections. Or the associated pre-sheaf of sections. Either way.
Yeah, what is a pre-sheaf of sections? I don't understand the
Yeah,
terminology.
that pre-sheaf of sections. Yeah, this is a very good
The
discussion.
terminology, I don't
Yeah,
understand
yeah.
it.
Pre-sheaf, given a vector bundle. Now you give me a vector bundle. I take an open set, and I look at all the sections over that open set.
Okay.
That is a mapping from that open set to a space of sections. So that's a pre-sheaf. Okay. So to be precise, you gave me the vector bundle, and I have an open set, and I say I associate to that open set the sections of the vector bundle.
Yes.
Okay. Fine. Great. So that's just exactly this business here. Okay.
Okay, so you construct it, you think of it horizontally, you don't think of it vertically. That's
So, well, wait a minute. I don't know what you mean by that. So here's you, and now you look at all the sections you might have here.
yeah,
That's fair. That's exactly that.
You don't construct it vertically. You say at each point what you have. You say like, okay, I think I get
Okay.
it now.
And now you take the direct limit.
Okay.
And
you find vertically what it is.
okay, so now you take the direct limit of, I'll say, here's a point X, and you take all these things here. This is a very important discussion, and therefore I'm very happy to have it. So here's X. Now here was a fixed U, and here then are fixed sections over U. But now we're taking all possible U. So given a point in this direct limit, there is a U where this thing extends to a section, but no uniform U.
But you'll not get back. I mean, if you do this process of taking all the sections
Yeah.
and then take the direct limit, you don't get back the vector bundle.
Yes, you do.
You do?
Yeah.
I mean, in my head, you should get it back.
You do. You do.
Like
Because
the germ should be the thing above.
yeah. Let me say exactly how you get it back. So let's do it again. Start with a vector bundle.
Yeah.
Then over each open set you have the sections. Take the direct limit. And then have all these horrible direct limit stalks. Okay?
Stalks and germs are the same thing or not?
Hmm?
The word stalk and germ are the same thing or not?
The stalk is the collection of germs. In English, if you have wheat growing in the field, this is the stalk of the wheat.
Okay.
Okay. This is all possible.
Like the fiber.
The fiber. We call it fiber. Okay. Okay. It's a very bad geometric object, but let's continue on. Okay, you call it the fiber, if you like. Here's X. Okay? And now every point here has a realization as a section, but I don't know where, on some neighborhood of X. So it might have some realization here, that one. Another one might have a great big realization as a section. Okay. Now if I fix U here, okay, I ask which of these things has a realization over U. Now what does that mean? I have to define what it means a section now over U. And I define it as a continuous mapping here. And a continuous mapping I have to have a topology up here. And the topology is given locally by the germs. So an open set is a local section.
So you have to construct the topology. That's
Yeah, I really, and it's my fault for confusing you, I didn't want to talk too much about it. You really have to talk about what is the topology on the sheaf space. It is, I say always, spazio lazzanato. It means the horizontal pieces locally, the local sections of these things.
It's not God-given. You have to construct it somehow.
Well, it's yes and no. It's sort of a direct limit topology. Okay, it's really a direct limit topology, and then you say a section over U is a continuous map, which is a section. So in that sense, you're right.
I think I understand why it's not a vector.
In that sense, you're right. And there's a fundamental point here that if you go from this, make the direct limit guy, and then go back to the sections, right? They are equal, these two things. You start with that, go to the direct limit, then go back. They are equal if and only if the pre-sheaf satisfied axioms 1 and 2. Okay?
Yeah, it should be like this. I mean,
Yeah, sure. I mean, it's a formal point. You would prove it very easily. Okay? So, you asked again about the notation. I'll use this notation to emphasize we're really talking about sheaves.
So you start with an object, it satisfies some axioms, and so you change the letter. That's what you do.
Yeah, in some sense, this pre-sheaf is a different thing than the sheaf. But I mean, in reality, they're the same thing because axioms 1 and 2 are satisfied.
Yeah, that's what confused me. I mean, why did you change the letter?
Yeah, okay. But if you read the literature, this happens all the time. Okay. And by the way, this course, when I was a child in mathematics, we had to take 1 semester course in sheaf theory, which is horrible. Yeah. And so I'm just trying to put it into 1 lecture, everything you need to know. And I confused you by not explaining enough why I use that. Okay?
Yeah, it's getting much more.
Yeah, but no, okay. Then you have a short exact sequence. You build this cohomology theory. You have a long exact sequence cohomology, but all the spaces are finite dimensional. And I hope I convinced you, just using finite dimensionality, you can prove theorems. Okay? What you're not going to prove, that's what Qaisar is saying, you're not going to prove any fine theorems until you really know exactly what these spaces are. Right? Because right now there's some horrible space. Okay? Well, I think we should stop there, and I'll try to continue on in the afternoon. I'm glad we had this discussion.
Yeah, I'm sorry I asked.
No. You're not sorry you asked. You understand that.
Yeah, I understand better now what's happening. Actually, what I see in my head is like when you have a vector bound, you have a space, and something that is delimited, like when you take an open set, you have like two right lines. When you have a sheaf, those lines are like this because you don't know what happens. So the sections are defined not linearly somehow on the sheaf. I mean, you don't have a right delimitation on the
That's right.
of the pre-image of the open set. So the sections are defined on. I mean, you don't know on which open set are the sections defined. So you have something non-linear above.
In some sense.
And that's why I think it's a more general thing than the vector bound.
It is. There are many more. That's right. There are many more points here. Right. I mean, what you're saying is in each stalk, in each fiber, at each point, this is a convergent power series someplace in the neighborhood of that point. And the topology says you put them together so that they define a function. That's it. But the stalks themselves are unbelievable. It's very close to formal power, well, convergent power series is what it is. Convergent power series in one variable. Right?